Today covering 219's decision trees. So decision trees, as a concept of trees, they are made up of nodes and edges. For example, we might have something like this. A tree like that splits on this, like so. They are called decision trees because when you actually implement them, they are basically hierarchical if-else statements. Each node represents an if or an else, or an if-else statement. Or in some cases if else statements, with each leaf node being a classification or other label, a prediction. So you have a tree structure like this, which will eventually get you a prediction based upon a series of if else statements. They are very simple, but they are capable and used a lot. An example of such a tree is this one. There we go. So we see here we have the nodes. Each node has multiple children. This one has 3. This one has 2. This one has 4. 3. 4. I can't count. 4. The reason why these are useful is that you can you have at this point all possible outcomes for each choice, because they learn. The reason that these are useful is because they are able to learn. At first, they're empty, but during the learning process, they will choose specific features of the environment to split on. And then the order that they split on and the ways in which they split is how the tree learns, the decisions it makes. Because each node is a decision. Where those nodes are, in what order they are, is how it's able to learn over time. So, for example, we had a very simple tree for a logical type of thing. We say that y is equal to x. We say x or x1 or x2. A tree that could classify this accurately would be x2 equals true as our first node. We have 2 outcomes for this, yes and no. If it's over here, then we have true as our outcome. We predict true. We predict y equals true. If it's a no, then we have to check if x2, x1 is equal to true. If it is, then it is true. If it is not, then it is false. So you see here, these are the type of things that these trees are capable of doing. It's a very simple tree. But the way we learn this is by looking at the possible outcomes of each and identifying from the test data that if whenever something is true, it has to go down the yes path, or it has to produce a yes path and go to true as well. So this would be able to learn for this specific thing. Now, you wouldn't actually make a decision tree for this. It's so simple, and it's deterministic. You can just run it through a logical evaluator, and it would do the same result. So you wouldn't use it for this. But there are other circumstances where you would. They are pretty good for probabilistic circumstances. They also work on numerical situations. Say you have some value x, like so, and x is a numerical feature of the environment, and it can have multiple things. We might say that x can tell us a lot of information about what possible things we have. So we have different things. We have 3 outcomes, like so. 1 for if x is less than or equal to 0.5. 1 if it's less than or equal to 1.5, and 1 if it's more than 1.5. So if it's 0.2, it goes left to right, it check each one in turn. If it's 0.2, for example, it go down to this path over here, whichever this is. If it is between 0.5 and 1.5, it goes down the middle path, and if it's greater than that, it goes to the right path. That would be an example of what it is. And those values of where it's splitting, that would be how the decision tree is able to learn. Just to reiterate. Different trees work under different rules. You have all these different ways of doing it. One way is that you must always have for every single feature only a binary split. So you can only go left or right. You can't have more than 2. Other times, every single feature gets its own node, and there are k children if the k is equal to the number of values that feature can have. So if you have something categorical, for example, a discrete value might be some x is equal to either A, B, or C, and here k is 3, so the x node in the tree would have 3 children. In other cases, it might be you'd only have 2 children. You'd have x Like so, you'd have if x is equal to a, it goes this way, if it's equal to b or c, it goes this way, for example. So different trees have different structures, they're all valid. There are different algorithms for manipulating these trees. We see here, these are the three we need to care about. You don't need to get too much about all of this. Some of it we'll cover as we go through the topic, others just know they exist. So we see here, for example, the fact that ID3 uses information gain and C4.5 uses gain ratio is something we'll cover when we talk about information gain and gain ratio. So you don't need to look at too much of this, just know they exist. There is ID3, CART, and C4.5, which is an improvement of ID3. There is a bit of math we have to keep in mind before we go further, which is the expected value. As a reminder, this was covered in 111. It is basically a weighted average. So normally, if you're trying to find the average of something, you sum them all together, divide by the total amount of them. If you're trying to find 5 plus 6 plus 7, you then divide by 3, and that gives you the average, the mean of those three things. This would be equal to the mean of 5, 6, and 7. Weighted average works a bit differently. You say that sometimes you care about specific elements in the average more than others, so you give them a greater weighting in the total product, in the final value. So, for example, say you are having a coin flip, but right, it's not a fair coin. It is a biased coin. So we have for heads it is 0.6, and for tails it is 0.4. In this situation, we can't just add up the two things. We can't say if we say that heads has a value of 1 and tails has a value of 2, the average roll here is not going to be. Actually, tails has a value of 0. The average roll here is not going to be 0.5 as it normally would be, because 1 adds 0 divided by 2, because it's more likely to get heads and tails, so that's going to shift it a bit above 0.5. So in this case, what you would do is, okay, these are the probabilities rather. There we go. The probability is two things. So what you do is you take out the total value. Okay, say for heads, we do 1 times by its weighting, which is its probability, 0.6, plus the 0 times by 0.4. If you put that in a calculator, you get 1 times. Oops, that was not right. Times 4. 0.6, which makes sense. Could have done that in my head now I think about it, because we are timing this one by 0. Oh well. Yes, 0.6. So it shifts upwards. In fact, if we were to change this to have been set 2, it would then be this by 2, which would then equal for 1.4. So the average in this case, if this was 2, would be 1.4. Sorry, not the average, the expected outcome. But the expectation, other times written. If you remember, it's something like if it's f is a random variable describes this event of heads or tails, we would say the expectation of f like so, and that would be equal to 1.4 or 0.6 if it was 0 as a value for t. So expectation, useful concept. Moving on, we have this concept of how we can, information storage and how we can represent things. We see this table here. Now, the slides don't explain this. I'll be able to find anything online that explains this. So if somebody else knows this, put in the comments, put it in the channel, whatever. But this only works if the probabilities follow the binary progression. Remember, you have 1, 2, 4, 8. It also goes the other way because it's 0.5, 0.25, 0.125. Yeah, it halves every time. Same, it doubles every time in the other direction because it's the powers of 2. And the in the decimal place, you just go to the negative powers of 2. So this is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and so on and so forth. So the probabilities are all fall into those ranges. You can use this algorithm or this equation to find out what this. So we see here, if we were a more naive approach of trying to store all these values for each possible event to represent which event it is, basically a flag, you're saying which event it is, and we want to be able to store this in some way, or to communicate in some way which event is happening, you might do something along the lines of just a set number of bits you would have, for example, this might be event 0, 0, this might be event 1, but then you've run out, so you're going to have to add more zeros. And then this might be event 1, 0, and then 1, 1, for example. Which will take, on average, 2 bits. So we're going to take 2 bits to do this. This technique, you see here, this has only 1 bit associated with it. This has 3, this has 3, and this has 2. The idea is, since the 1 bit is much more common than the 3 bits, they have a 1 in 8 chance of occurring, so 2 in 8 chance of having 3 bits, 50% chance of having 1 bit, and a 1/4% chance of having 2 bits. The expectation, if you find the expectation for this, it's going to be the 1 times 0.5, 2 times 0.25, 3 times 0.25, 125, plus again, on and on. So you add all those different terms, and you get 1.75. So the expectation for this is 1.75 bits on average. The expected value is lower. So you're using less information. What I struggle with this is how you actually implement it, because we have to have a set number of bits so the computer knows what it's reading. If it doesn't know how many bits something is represented in, it just doesn't know how much memory to read. So unclear on how that works, but presumably it works, otherwise it wouldn't be in the topic. So if you get a question like this, we're saying how many bits are required to store this information, it's this process. The equation for it follows this thing here. There it is. This is a specific to this case, and the generic way of doing it. Well, look, not the generic way, but another way of doing this would mean you don't have to know all the same information. You don't need to know how many bits ahead of time, because we're trying to find that out. Rather than doing this and saying, okay, we can put random values on all of them, find the one that lowers it the most, that would work. What instead we can do is use logarithmic arithmetic, which gives us this equation. There we go. Which basically says that rather than timesing the number of bits, you times by the log 2 of the probability. So we see here, in order to get this value, you times it by 0.5 times the log 2 of 0.5. Here, 0.25 times by log of 0.25, 0.125 times by log of 0.5, and so on and so forth. This one happens twice. And that will give you the same value. This will still equal 1.72. 1.75. And that'll work regardless. So regardless of knowing how many bits ahead of time, you don't need to know how many bits ahead of time. You can calculate it using that equation. And the generic form of that is equal to, we say that is the negative, because logs typically put out negative values, the sum of this probability of some outcome. Remember, say for example 0.5 is a probability of Trek occurring, so it's a probability of, this would be Y. Trek, Specialized, Cervelo, and Sirota. Corello, I'm not sure. They would all be the Y's in this case, the outcomes, the predictions we might make. So the probability of each prediction multiplied by the log 2 of the probability of that prediction. In some cases, you would put brackets here. Like calculators will put brackets after log 2 because it treats a function. You do this. So you say, and this is for all y from y. So every possible prediction you can have, you try for all of them, and then you negate it at the end. So you have to do this negation, because otherwise you get a negative value. Just due to the way logs work. So this will give you the same thing as above. It's a more generic way of doing it. What it will also give you is it will lead you to getting entropy. So entropy. Oh, and by the way, this gives you optimal. So this is the optimal division of bits you can have. This equation will always tell you the most bits you can have. So the most expected bits you can have. So it's the best approach. So entropy is called a measure of uncertainty. So if you have some random variable f that can have 3 different values, it measures how uncertain f is. For example, if it's very random what value f has, then it's going to have a high entropy. If it has if it's to 95% chance of having outcome A, and then 0.5, that's not 5 of having B, it has a low entropy. because it is almost definitely going to be A. It's quite certain what its output is, so its entropy will be low. I believe. It slides unclear about this, but basically, it's how uncertain a value is. That example might not be exactly correct. If we see the graph here, actually, which I've done it wrong. Here, so we have a entropy function for some binary random variables who has two outcomes. We see that the entropy is written with a h, so h of y, which is our prediction, which is then on the y-axis. On the x-axis, we have the probability of each of y's, or of y being a specific thing. We can see if y is at 0.5, entropy is highest. Oh no, I was correct. Yes, I was just reading the graph. So if entropy is at the middle, it's very high entropy, which is bad. But if entropy is very deterministic, so it's very likely to be a specific way or very unlikely to be a specific way, entropy is low. So as I said, so if f is equal, if f equals a, and the probability of f equals a, that's what I meant to say, is equal to 0. I can't write. 0.95, that's going to be a very low entropy because it's very deterministic. It's almost definitely going to be A. So entropy is a measure of how uncertain a variable is. So if it's 0.5, then it's very difficult to say which way it's going to go. As it's also going to one of the extremes, it's more likely to be deterministic because more often than not, it's going to be a specific value rather than multiple values. And yeah, this works with binary. If it were if it had 3 outcomes or 4 outcomes, then it'd be the peak points where everything was 0.3 recurring, a quarter, and so forth. So the peak points is going to be associated with the points where it's equal a uniform distribution of probabilities. So that's entropy, and it's the function for it is the same one we saw before. It's this. So entropy of some random variable is equal to that, which is the same one for what we just figured out. There is also conditional entropy, because we don't always know all these values, but we do often know conditional equations. Given something, given some evidence, given some features we observe in the environment, then what is the entropy? So we have conditional entropy, and the equation is much the same. It is, I've lost it, there it is. There. So we can say, for example, that the entropy for y given x is some observed value is equal to the negative of the sum of the probability of y being that thing and x being a particular thing as well, times by the log of the same thing, all summed together. That gives you the entropy conditionally of x. So yeah, that's entropy and conditional entropy. When we have entropy, this concept of entropy, we can then use that to track what's called the information gain. And this is where we start getting to how these things learn. There are multiple heuristics we can have. For example, decision trees sometimes use Occam's razor as a heuristic. Basically says the simplest approach is probably the correct approach. Which is an okay heuristic, but it's not great. And oftentimes it can be superseded by using this information gain. Information gain simply is a function, typically written as info gain, that takes in two things, a D and an S. So D is the training data. It's a set of training data we're working with currently. And S is a potential split. So we're saying this is a feature that we're thinking of splitting on. So for all the features in the environment, this is one of them we can think splitting on. So we say for that, for example, with the first one might be an environment which has 3 things. S could be to A, and it has multiple different possible random values to the random variable. We're saying we're thinking of splitting on A. What is the information gain of splitting on A? Because we want information gain to be as high as possible. Because basically it's saying how likely is it this is going to reduce the entropy. How much information do we gain? How clearly cut? How much more deterministic are we if we split upon this thing? Because we would do this for A, we do it for B, we do it for C, and then we select the one with the highest information gain. So it is equal to this, and it is equal to basically the entropy. We typically use a subscript D here. You're saying it's this means it's in respect to a particular instance of D, rather than the entire thing. So it's being specific about a particular instance of D. So the entropy of this is the y. So the entropy of our y, so our actual value, our prediction, where it should be, our correct label. Remember, training data is a supervised task. So training data is in some set of things, x, then also a y. And that is each particular training data, that should be brackets, makes up that. So y is the accurate, is the correct label thing it should give us. We say what is the entropy of the correct label, minus the entropy of the minus the conditional entropy of that correct label for that, given the thing we are looking at. So in this case, we don't actually have a set 5 for S. You have to find all of them. It means a bit more work, but still the same process. And that gives us the information gain. So if we do this, we might say, okay, there's two things here. One of them gives us, say, 0.1 information gain. So we've gained 0.1. Another says we are going to gain 0.9. Which is clearly 0.9 is the better one. So 0.9 should be the sorry, not 0.9. The example we're given is something like this. We see here, I'm not going to too much in this process because it's, as I've already explained, this is the entropy. This matches up to this. This is this. So this is trying to find that value. Again, I've already shown how to find value, so I'm not going to go through it now. This is finding the entropy of the specific thing. We subtract them, we get this as the information gain. And in this case, we care about this one because it's bigger. We want the maximal information gain. So this is the split we'll have because we are choosing, do we want to split on humidity or wind? So we have a specific data set. Which one is it better to split on? Humidity or wind? Which one gives us the most information? Humidity gives us more, so we're going to split on humidity. And then we will split on humidity. Then we'll do the next nodes for each of its children. Say how can we split it next? We'll do the entire process again on the remaining features and keep doing that until we can get as maximal information as possible. The problem with information gain is the process of finding all these values typically comes from having a table and all these a large table of sample data. And if you don't have much sample data, it's not going to be very good. So it's that's not me. It is biased towards large samples. Well, it's biased towards tests with many outcomes, so large samples. It wants lots of data. It's if you don't have much data, it's not going to be working very well. If you have a very specific, if you have one basically, it will just follow that one directly. Because that will give it the most information. It will work, but it won't work very well. The structure it will produce will not be a good one. So you need lots of data and lots of samples for this to work. To help with that, you can use what's actually called gain ratio, which is the same process. So gain ratio, it also takes a d and an s, is equal to the info gain of d and s divided by the entropy of s. For the specific example, what's the entropy of s? You divide info gain by that, and that just normalizes away from the specific example, and hopefully it makes it a bit better. So in this case, this is what's called the splitting criterion. This is the thing that we choose how to split on. So we hide the biggest gain ratio is the one we go for. This is the one that C4.5 uses, for example. Remember, C4.5 is a improved version of the one I can't remember the name of. ID3, that's the one. ID3 just uses information gain. So this is the way that is improved, or one of the ways it's improved. So ID3 is information gain. C4.5 uses gain ratio. Okay, so moving on. We've looked at how we can split a specific node. Now we need to look at how to know when to stop. How do we know when we've finished searching? So there's two basic things we care about. So what's called the stopping criteria. So everything we've looked at was the splitting criteria. Now it's stopping criteria. So there are two instances we have to keep in mind. So candidate splits, so possible features left that we can split on. If you've already split on everything, you can't split on anything else, therefore you're done. And all those are the case of, by a particular point, you've already categorized everything correctly, so you have 100% accuracy. So those are the two possible stopping criteria we can work with. We have to work with them both. Because if you've already got basically if you have a thing that then gets you to something here, which gets you to, I don't know, 5 which are categorized correctly, 4 which are not. This gives you 6 which are, 3 which aren't, for example. The fact that they add up to 9 doesn't matter. And then you might have another one when this gets it, it might get you what's left here. We have 9 here, so this might get you to 7 and 2. So this does have to match up to 9. This would be 18. Because you can't add in instances. You have 9 over here, so you have to have another split of 9. So this way might get you 9 if you fall that way, and so on and so forth. Actually, no, it wouldn't give you 9, wouldn't it? It would have to give you, they have to both add up to 9, pardon me. This might get you 4 and 1, and this might get you 3 and 1. That's 9, 5, 6, 7, 8, 9, yes. So if you keep doing that, eventually you might get a split which has 4 over here, and where everything is split appropriately. In this case, you're no longer uncertain. You very clearly have a set outcome. This is classifying everything in this one as whatever this is. Everything in this one as whatever that is. There's no uncertainty here. This one mixes them. It doesn't know for exact. It knows they're kind of shifted towards the left-hand side, but doesn't know for a fact. Down here, it already has classified them correctly. Once you reach that point, there's no point splitting further because you've already reached what you're trying to do, which is to properly predict them. So this says for all the trained data, we are accurately able to put all of them into that one, or the other one. It probably splits them down the middle. Well, not down the middle, but it splits them accordingly. So once you reach that one, there's no point going on, and once you've run out of possible splits, there's no point going on. So in order to know but once you have that other possible trees, one thing that's important to know is accuracy. So accuracy is a function we use. That's not it. Accuracy. It takes in a D and an M is equal to. Okay, by the way, this is the model. So this is the decision tree. So it's the trained model, hence model for M. And D is a set of sample data that we're trying to use to test how good the tree is. It is equivalent to, or is equal to, the size of the set of M. So we say M of X. We apply something X from our data set, and we try and find some output. So in this case, L of X is the true label of what it should be, and it is all of the instances where the predicted label is the true label. So this is predicted, or prediction. This is correct. So we want the set of all things which accurately predicts, and then where X is an element of D. So we want the set of all things that accurately predicts, and we want the size of that set, the cardinality of it, and then we divide it by the total size. So it's the size, the number of correctly predicted data sets divided by the size of the total data set. And there's a question here of what D is. We'll look into that more accurately in a second. We saw what types of trained data we should be dealing with. There's also the concept of error, which again takes in a D and an M. This is the opposite of accuracy, which is 1 minus the accuracy of a D and M. So error is just 1 minus the accuracy because it's the opposite thing. If accuracy is 0.7, error is 0.3. So we have to be careful on what data we're using here. Because training data as the data is used, these are things supposed to generalize and work on data it's never seen before. So typically it's a good idea to find this accuracy based upon some other test data. So when you're devising all your test data, your training data, it's good to take some aside and never let the model see that data, so that when you need to test on how accuracy it's doing, how well it's learning, you can do data it's never seen before, and that it won't learn on. So to be, if you have, this is all possible instances it might see in the entire thing, including where it's working. Down here is the things that you have access to. You then want to split it to some point. Sometimes it might be 50-50, sometimes you want a small subset. Some of that's for training, some of it's for testing. So you get that that result there. The test set is what you use for accuracy and determining accuracy. The idea is that you want to get as high as possible on the stuff it's never seen before. So as well as all that, we've seen before that these are the two stopping criteria we can have. Sometimes, though, we can stop earlier. We've gotten good enough that we've dealt with it all. So you want the concept of pruning. Basically, there are bits of the tree that don't actually add too much to the overall thing. So we can get rid of them safely and barely, if at all, reduce the total accuracy. The concept of pruning, of getting rid of leaves of the tree or branches of the tree. Hence, like gardening pruning. So in this version, as well as how you have all those things, you have your test and data, your training data and your test data. You then split the training data down further into another something which is called tuning. So this is your training. This is your test. So tuning data is a validation set of training try this again, shall I? The tuning data is a validation set, which is a subset of your training set that is held aside and not given to the thing. It is used to help better improve and fine-tune the entire model. So it's not used for growing the tree, it's used for pruning back the tree, making it smaller and more efficient, size efficient. C4.5 uses pruning. The idea is that you split your given data into training and validation sets, that's your tuning sets. You grow the complete tree, and then you will do that until pruning is harmful. So you then prune it, and you try all the ways of pruning it, and keep doing that, making it smaller and smaller and smaller and smaller until pruning becomes a harmful process, and it starts negatively impacting the tree. So you will have a tree such as this, you'll grow the tree, like so, do this and this, and you might say, okay, what if we get rid of this bit? And he says, okay, well, look at the accuracy again, it hasn't been too bad. What if we then get rid of this bit? Still pretty good. This on its own is a very good thing. If we get rid of this, well, that's gone too far. We need to leave that in. That type of process. So I believe that's everything on decision trees. So this one's smaller. I'm testing the idea of having a smaller. Pardon me if I'm unclear today. For some reason, my throat is very dry. It's really messing with my ability to talk. But yes, I'm trying another way of doing this, which is smaller, more bite-sized videos on specific examples, just because the slides for 219 are so horrific. They are a pain to get through. They're so unclear, and they produce so many different things. So I'm trying this way, so I don't have to spend so much time preparing and then delivering. I can do a bit of preparation, a bit of delivery, bit of preparation, bit of delivery. So, yes, that's everything for this session. Good luck with exams.